Hi, everyone. Welcome to today's presentation, Harnessing Climate Data for Better Decision Making. Today's guest speaker is atmospheric scientist Adam Sobel, and our host is Todd DeVoe. These webinars are produced together by SpeaknSpark and the Emergency Management Network. My name is Holly Manny Ioskui. I'm the founder of SpeaknSpark, and I'm all about making it easier to find and share expertise across disciplines in one location. Thank you for being here with us today. We appreciate the time you've taken to join us, and we want to give you high quality content that fosters your learning. The format of today's webinar will be approximately a 30-minute presentation followed by a Q&A session. Today's webinar is a live event. We have enabled the Q&A feature, which is a part of your Zoom screen menu, most likely located at the bottom of the screen. For those interested in networking or connecting, you can use the chat feature. You can share where you're joining us from, and we suggest sharing your LinkedIn profile over your email address. We won't always be monitoring the chat, so the best place for your questions are in the Q&A section. You can enter the questions at any time, and we will be addressing them during the Q&A session. And if you miss anything today, don't worry, we are recording this webinar and we will be sharing it on our social media channels as well as a follow-up email. So let me introduce the host of today's webinar, Todd DeVoe. Todd DeVoe is an emergency management educator and the host of numerous podcasts, including the newly minted Todd DeVoe Show, launched through the Emergency Management Network. Todd is a lifelong learner, and he's a graduate of the National Emergency Management Executive Academy. He continues to research and write about important emergency management issues, crisis leadership, business continuity, and community resilience. Todd's an active member of the International Association of Emergency Managers and president of Region 9, as well as a SpeaknSpark speaker. Thank you, Todd, for hosting this important topic today.
Thank you so much for having me here today, Holly. It's a pleasure. And one of the things we're speaking about here is climate change and why it's important, right? And this is going to be the series that we're going to be focusing on here with the Leaders Speak webinar series. And our first one here, obviously, is we're going to get into decision-making models and why we should look at climate change. Again, whether you believe it's human-caused or naturally occurring, climate change is something that as emergency managers and crisis managers, we have to really take into consideration when we're building our plans, trying to figure out things to mitigate, for the climate as well, for hazards, and also taking into the human cost, excuse me, the human condition as well with climate. So we're working hard to put together the next few webinar series. It's happening live in digital format here. Thursday, May 19th is going to be our next one. We'll get into what that one's about here in a minute. But first, I want to thank our sponsor, the Natural Disaster and Emergency Management Expo, for sponsoring Leaders Speak 2022 webinar series. We're excited to continue our relationship with them and go check them out and see all the things that they are doing to help the emergency management profession. And lastly, we want to let you guys, I know Holly just brought it up, the idea of question and answers. It's really critical that you do put it in the Q&A area down below. If you put it in chat, we might lose you, but chat is great for just kind of conversing about what's going on and also any logistical issues that we might have, whether it's sound quality or whatever. But that being said, I want to introduce our guest. So Adam Sobel is the atmospheric scientist and earth and environmental science professor at Columbia University. And Adam studies weather and the climate, right? So which is a great person to have to really kick this off with a focus with extreme weather and events. And particularly interested in these topics, he is very interested in this with the tropical weather. He is the director of Columbia University Initiative on Extreme Weather and Climate Change. He's developed novel methods for essential mechanisms and understanding the connections between weather and climate. And Sobel was featured in the 2012 NOVA documentary Inside the Megastorm about Hurricane Sandy, and later published his book, The Storm Surge on Hurricane Sandy and Our Changing Climate and Extreme Weather in the Past Future, 2014. And he also hosts the podcast Deep Convection. Adam, welcome to the program.
Hi, thanks, Todd. Thanks for having me.
Absolutely.
So, oops, what happened there? Or is that? Are you guys seeing my screen now?
Not yet.
Something weird happened. Let's try that again. I didn't like it, just blew up and I hadn't shared yet. Let's share the screen. Let's do that. Share, and let's go to full screen. How's that?
Yeah, we got you 100%, Adam.
Okay. So, right. So let's start. Thanks so much, Todd. Thanks, Holly, for having me. It's a pleasure to speak to this group. I'm not an emergency manager, but I have great interest in what you all do, and I hope that I can say some things that might be useful and spark some conversation. So here's my title. Let's get right into it. So here's my outline, just 2 bullets. There's 2 parts to the talk. I want to first give a broad overview of climate change and extreme weather. So how is the fact that the planet is warming affecting different kinds of extreme weather events? And there's things we know, there's things we don't know. And I'm going to try to say something about both of those, and also to explain a little bit about why, to give some sense of the science behind why there's different degrees of uncertainty and why we make some of the different kinds of statements we make, and why there isn't a single answer to the question, how is climate change changing extreme weather? There's a bunch of different answers. And then after going through that, which is pretty general material, I'm going to do a case study of one specific event to try to make things a little more concrete and maybe a little closer to the specific interests of emergency managers, which is to talk about what happened with the remnants of Hurricane Ida in New York City in the end of August 2012. So, okay. Right. So here's just to get us all on the same page. The climate's getting warmer. This is a slide, and I'm going to show a bunch of slides like this that are from the most recent report of the Intergovernmental Panel on Climate Change, the IPCC, the 6th assessment report called AR6. So this is the latest assessment of the world's climate scientists. And this shows the time rate of change in degrees Celsius. Sorry, so it's degrees Celsius is a little less than 2 degrees Fahrenheit. And 0 is like the long-term, historical average in the past. So 0 is like the baseline. And this shows how the temperature has changed, the top graph. The global mean, global average surface temperature of the Earth. And we can say it increased, especially in the early 20th century, then it was flat for a little while, and then it increased since the late 20th century to now. By now, over a degree Celsius, couple degrees Fahrenheit of global warming. And although there's lots of ups and downs, you can see the long-term trend is clearly up. And in particular, as the bottom graph shows, if you just average over the decades, and there's different data sets shown here that give slightly different answers, but in all the different data sets, every decade of the last 4 has been warmer than any before it since 1850. So the climate's definitely getting warmer. We know that. We also know that it's due to human emissions of greenhouse gases, carbon dioxide and others, methane, nitrous oxide, et cetera. And this is another plot from the IPCC report showing that what's projected by the world's climate models for the future, as well as the past. So the historical sea surface temperature, global mean surface temperature is shown with the 0 being what the average was from 1995 to 2014. And so you can see the history going up to the early, to now more or less. And in the future, these other curves that are averages for many climate models, and the sort of shading shows a range from different models, but the different curves are from different scenarios. So these SSPs, shared socioeconomic pathways, are different assumptions about how much greenhouse gases we emit. So the more greenhouse gases, that's the sort of darker, redder colors, we get more global warming. The next couple decades, it doesn't make that much difference, but then after that, because that's mostly due to the carbon we've already emitted. But what we do in the future, the models give different answers. That's why there's a range, but you can see that in the long term, the big uncertainty is what human beings will do. That's what differentiates these different scenarios. So the low numbers are if we strongly reduce greenhouse gas emissions to 0 soon, then we get these curves that go flat and even drop a little by the end of the century. And if we don't, and we keep emitting like gangbusters, then we have much more global warming. In fact, probably really, really catastrophic levels of global warming if we have these worst case scenarios, which hopefully we won't. I think the most likely one is somewhere in the middle here. But anyway, that depends on what we do. Okay, so now when we want to talk about extreme weather events, we got to talk about the consequences. So the way that the planet is getting warmer, we know for sure. We add more carbon dioxide, it gets warmer. But then there's a lot of other things that follow on from that, and some of them we understand better than others. And how different extreme weather events change can depend on these different factors in different ways. So one thing that we know pretty certainly is that a warmer atmosphere has more water vapor in it, all else equal. And this is a consequence of basic physics, which I'll say a few more words about later. But these are just observations to show it. So this is not now projections. This is observations. The total column water vapor is the total amount of water from the surface up to the top of the atmosphere. If I took it all and condensed it into a puddle, it would be, some tens of millimeters thick. And how much is that increasing? So the observations for the planet of that total column are on the left, and you can see that it's going up. So there's more water vapor in the atmosphere. And then the lower right, again, this is from IPCC. These are the rate of change. It's the trend over the last few decades in the surface specific humidity. So not relative humidity. The relative humidity might not change much, but the specific humidity is a function of temperature. Rather, the saturation value is a function of temperature, to be a little bit technical for a moment. So these greens, to cut a long story short, mean that the absolute humidity is going up. The amount of water vapor in the Earth's atmosphere near the surface is increasing almost everywhere that we have measurements on land or over the ocean. So that's pretty simply related to temperature. So some things will follow from that. Another thing we know for sure is that the sea level is going up. So this is a plot showing observations again, no model predictions in here. This is sea level relative to a historical, a long-term past value, a global average sea level in meters, sorry again for the metric units, but different data sets that give slightly different answers in the earlier, in the early 20th century, but then in the later part where we have satellite data that's very accurate in addition to tide gauges, and we see this steady rate of sea level rise, and that affects coastal flood risk, as we'll talk about later. So how much the sea level will rise between now and the end of the century or further out in the future is uncertain, but we know it's going to keep rising. There's zero chance it's going to go down, and so that affects our, our risk from some kinds of extreme events. On the other hand, there's some things we don't know. This is a map showing how our climate models, this is again an average picture from many, many climate models, which are complicated computer models that simulate the atmosphere and the ocean in detail. And this shows how the average rainfall on the planet is expected to change under one particular warming scenario by the end of the century. This is a worse, not the very worst case, but a pretty bad warming scenario. But the main point is the pattern. You see that some places are getting rainier, that's the green. Some places are getting drier, that's the reds. But the diagonal lines mean that the models don't agree. So at the high latitudes, the models are agreeing that it's going to rain more. But a lot of the tropics and even the mid latitudes of the United States, these diagonal lines mean the models are not in agreement about even the sign of the change, even whether it's getting wetter or drier. And so this is because it depends on the atmospheric circulation, which is related to the temperature in complicated ways that we don't completely understand and the models don't completely agree on. So anything that depends on that is much more uncertain than something that depends just on the temperature or water vapor. That's the message I want to get across, and we'll come back to it. So as I've been saying, extreme weather is influenced by different aspects of climate change, the certain ones and the uncertain ones. So when we talk about different kinds of extreme weather and we ask, are they getting worse because of climate change? The answer is, it depends what kind of event we're talking about, and there's different factors at play. And so I'm going to give a few examples now. So heat waves are the simplest one. It's getting warmer, so you'd expect more heat waves and worse heat waves, and that's what's happening. And this is not, I'm not showing statistics here, I'm just showing a map from one extreme event that happened last summer, June 2021, the heat wave in the Pacific Northwest, where we had 120 degrees Fahrenheit, I believe, in Portland, Oregon, which is just nuts for that city. Very, very high temperatures in British Columbia. We had terrible forest fires with this event. And, a heat wave just means it's defined a little bit different in different places, but they all amount to, you pick some threshold, 90 degrees or whatever, and you say if it's warmer than that for some amount of time, whether it be a day or 2 days or 3 days, that's a heat wave. So once you set your definition, if the whole planet gets warmer, and the weather is still coming and going. I mean, a heat wave is a weather event, but it's starting from a baseline climate. And if the baseline climate is warmer and everything else stays the same, you're going to get more heat waves and worse heat waves. And it's not exactly that simple, but it almost is. So heat waves, I'm not showing you all the statistics, but heat waves are getting more frequent and more intense. That's what the models predict. That's what we observe. And so that's the simplest one. Wildfires, for example, are a little more complicated, because a fire depends on how wet the ground is and the soil is, and the rainfall, as we saw, is complicated. How well we can predict drought varies, and for example, the recent droughts we've seen in California, to the extent that it's raining less, some of that is natural variability, and the global warming signal is hard to see. But because it's hotter, any of the water that's already on the ground or already in the wood that's lying on the ground will evaporate quicker. And we know it's hotter because of global warming. So that by itself makes fire-prone places more fire-prone. And this is what we see. This is from a paper by one of my colleagues, Park Williams, used to be at Columbia. Now he's moved to UCLA, I believe. And he shows that in the last 50 years, California, the amount of average annual burned area in California has increased fivefold, with more than an eightfold increase in summer forest fire extents. These are huge changes. And you can see if you look at these graphs that they're going up and down a little bit over the last 100 or so years, but especially going up now. And the red shows predictions from the last round of climate model reports. So this is both due to temperature and aridity. And fires are complicated. There's a lot of fires are started by people. They depend on forest management. It is by no means just a result of the climate, but climate is one factor for sure that's driving more wildfires. To go the opposite extreme, so tornadoes and hail are an event that emergency managers have to worry about. Tornadoes especially can kill people sometimes. We know rather little about how these are affected by global warming because they're not related to a temperature in a simple way. Basically, you get tornadoes and hail from severe thunderstorms that form under particular conditions. And when it's hot and humid, it favors those conditions, and that's happening more often. But you also need something called vertical wind shear, which happens in the US plains, for example, because it's underneath the jet stream in the springtime when these storms form most often. And actually, our climate models predict that will happen less in the future. So you need two ingredients to get tornadoes and hail. And we think that those are changing in opposite ways due to global warming. And so which one wins is a subtle matter. And there's research studies that has said both things, and the data is inconclusive. So this is one of the things we don't understand very well. We know there's tornadoes, we know there's hail, we know there have been some very active years lately. There may be a climate change influence there, but we don't have a strong scientific handle on that yet. Hurricanes is a topic I've studied a lot. I'm not going to talk at the length that I could, but just to say a few things about hurricanes. This is a summary. I'm not going to show you all the data to justify all of this, but there's a couple of plots at the bottom. I think maybe I won't talk through those graphs in detail in the interest of time. I'll just give you the bullet points. So we're pretty sure that as the climate warms, hurricanes get stronger in terms of their winds, and they produce more rain. The rain is quite a strong conclusion, and that's because there's more water vapor in the atmosphere, which we know. Hurricanes are very good at squeezing that water vapor out. So even though it's hard to measure rain well in a hurricane, we're pretty confident that they're producing more rain, and that trend is going to continue. They're also getting stronger. We see that in the observations, although they're a bit noisy, but we can see it in the studies most of the studies that have looked at it. And we have good reasons, not just from climate models, but also from our theoretical understanding, which I could talk at length about, but I won't, we understand how the climate affects a hurricane such that if it gets warmer, hurricanes can get stronger. On the other hand, we really don't know whether there should be more hurricanes or fewer hurricanes in a warmer climate. When I started my career, we used to think a warmer climate would have more hurricanes. Then a lot of our best models started to say that we should have fewer. And now some of the best ones say we should have more, but they don't agree with the other ones. And we don't have, unlike rainfall and wind strength, we don't really have a theory. We don't have a physical explanation that everybody understands for why we have the number of storms we have, which is about 80 or 90 per year, reaching tropical storm strength in the Earth's climate. So we really don't know that. And that's a big uncertainty. There have been some changes also found in where the storms are going and how fast they move from one place to another. But those are interesting and being studied actively, but still a bit hard to say conclusive things about them. On the other hand, so that's the story with some certainty and a lot of uncertainty mixed together, depending what question you ask about hurricanes. I'm saying some aspects of them are getting worse, but on the other hand, you might be less likely to get one, at least in some places, or we don't really know. But on the other hand, something we do know is that a lot of the worst disasters from hurricanes are caused by coastal flooding. That's storm surge. That's when the wind blows the water onto the land. And this is an image of the Jersey Shore, which is a barrier island in Hurricane Sandy, getting totally submerged in a storm surge event. And because the sea level is rising, okay, and this is now showing projections out to the future of different warming scenarios and sea level rise, with numbers going up as high as a meter, which is like 3 feet by the end of the century in some of the worst scenarios, or even more than that. If you really take the worst case, this is an envelope of different estimates of sea level rise. In Sandy, the storm surge was 9 feet on top of 5 feet of tide. So it was 14 feet of water above low tide in New York City that caused such an extreme damage. If you have 3 feet of sea level rise, then the water starting from a 3 feet higher place, you only need a 6 foot surge to make the same destruction. And if everything else is equal, you're going to have a lot more storms that are going to, because it's a lot easier for a storm to make 6 feet of surge than 9 feet. So in other words, even though there's a lot of uncertainty about the storms, we know that coastal flood risk is going up because we know sea levels going up. So that's something we do know. What about rainfall-driven floods, floods that are in freshwater floods caused by precipitation? So to talk about that, I want to talk about it in the context of this one event, which was Hurricane Ida in the Northeast, which was a rain event. And I'm going to use that event as a context to say something about how global warming affects rainfall and freshwater floods. And then I'm going to say some more things about just what happened in this event, the story of it. And I think there's some interesting things there that we could talk about with emergency management. So here's first just some basic facts. This is a map. This was a forecast map issued by the National Hurricane Center on, I believe, Sunday night, August 29th, 2021. This is actually the 16th anniversary of the landfall of Hurricane Katrina in New Orleans, kind of spooky. And so it was making landfall. That's what you see down there in Louisiana. It was quite destructive there. But at this time, the Hurricane Center was predicting that over the next 5 days, you see the cone of uncertainty there, that the storm would weaken quickly. So it goes from H for hurricane to S tropical storm, D to depression, which is getting weaker. And that it would track then over the continental US as a weaker storm, and then cross over the center, crossing over basically New York City with this cone of uncertainty, but the most likely tracking over New York City. So this was very, very well predicted. This turned out to be pretty much exactly what happened. This was a forecast. I'm not showing this is not after the fact. This was actually the forecast at the time. So NHC did a great job. And as the storm got closer to New York, as it made it up through Pennsylvania, New York, New Jersey, it interacted with a frontal system, a mid-latitude, normal weather system coming through here that would have produced some rain anyway. But the interaction of the two caused really, really heavy rains and flash flooding that ended up killing 50 people in the New York City metro area, New York, New Jersey, PA, and southern New England, which is a bigger number than even Sandy did. So it was quite shocking what happened, actually. So here's some data. I'm a meteorologist. I like to show weather data. So this is from the so-called CoCoRaHS network, which is a network of rain gauges that includes the Weather Service, but also volunteer gauges. And you can see the numbers in this color scales here by the right. This is the totals for the 24-hour period when Ida was passing through. And you see lots of numbers up around 5, 6, 7, 8 inches, really, really, really high rainfall totals across a wide swath across PA, North Jersey, New York City, and southern New England. So really high, that's a lot of rain to happen in 24 hours. But what really made the disaster, I'm going to argue, was not how much rain fell in a day, but how much rain fell in an hour. So these are numbers from the New York City Mesonet. This is a state-operated rain gauge network by New York State that shows the most rain that fell at a single hour at these various stations. You can see 3.8 inches in Central Park in 1 hour, and a bunch of other stations around the city that had numbers about that high. Now, this is a really good test case because just 10 days before, we had Hurricane Henri pass through through New England, east of Long Island, and we got outer rain band of it in New York City area, and it produced similar amounts of rain in the daily total. In fact, Central Park in Henri got 2 inches in an hour for 2 hours in a row. So it got 4 inches over 2 hours. And it caused some flooding and little problems in the subways, but it didn't kill a lot of people. I don't know if it killed anyone. It may not have killed anyone, and it didn't cause anywhere near the same damage. Ida shut down the subway system the whole subway system for a good period of time. Henri just caused a couple local problems. So big difference between a daily total of 6 or 8 inches, but with it spread out over more hours versus if you get it compressed into just an hour or two, you get a big damage. So we had a really good demonstration of just how much difference the hourly rainfall makes for New York City when it comes to flash flooding and damage. And the climate change connection, this is relevant because, and I'm just keeping an eye on my time here, so here's how we expect heavy rain events to change as a consequence of climate change. The left plot shows, from a paper that's now about 10 years old, but it's still more or less correct, an estimate of, for each degree Celsius of global warming, by what percentage do the heavy rain events get heavier? And they get heavier because there's more water vapor in the air. And I don't think I'm going to explain all these curves. There's some interesting ideas about atmospheric physics in these. The main thing is, these are climate model projections. A range of different models give this blue shaded range, and the best estimates are somewhere in there. It's like 6 or 7 degrees increase, 6 or 7% increase in how much rain falls in the heaviest events on the daily time scale per degree warming. So every degree of Celsius that the planet warms, we think a rough ballpark estimate is you get about, your heaviest rain events get about 6 or 7% heavier. And that's due to the basic physics of water vapor, that that's the rate at which the amount of water vapor you can have in an unsaturated, before you reach saturation, increases with temperature at about that rate. So it's pretty basic physics, explains what these models are doing. And here's some observations. This is from the US National Climate Assessment, the most recent ones. This is now observations. This is not climate models. And this is showing the trends over different periods, either the whole 20th century to early 21st or since 1958. And it's different measures of extreme precipitation. But let's look at the 99th percentile. That's the heaviest rain event out of every 100 days. So that's what this, anyway, that's one measure of how heavy the heaviest rain events are, is the heaviest 1% of rain events. And you can see it's blue basically almost everywhere in the United States. Heavy rain events getting heavier, but especially in the Northeast by 40, 50%. So it's at least definitely qualitatively consistent with what we expect. Maybe actually this is a heavier increase that we're seeing in the Northeast than what is predicted globally, but that's just what that's what's just happened. Like, we can't claim that all of that is global warming, but I think it's very, very likely that a lot of it is. But that's daily, and I just argued that the hourly was more important. And this is a complicated, lot of words on the slide. You probably shouldn't try to read it all. This is abstract from a technical paper in the atmospheric science literature. But what it says, to boil it down to a bottom line, is that this is some research from the Netherlands and the UK, that hourly extremes increase faster with warming. So 6 or 7% for the daily rainfall, but the amount that can fall in an hour may scale even faster with global warming, so that we can expect flash floods to get worse at an even bigger rate. I think this subject is still relatively early in being studied. I don't think we completely understand this, and there's a lot more work to be done on it. And there's not that many data. There's not that many rain gauges that report hourly rainfall very accurately on a global scale over long periods of time to study this. And our climate models are not that good at predicting hourly rainfall. It's a little too fine scale for them. But it just suggests that these kind of events could be the kind that we see happening more and more, even more than larger scale events. So when you have the daily rainfall total is what affects the larger scale flooding, like with how the rivers rise and all of that and flood their banks. That's larger scale. But hourly rainfall extremes, you can have situations like what you saw in Ida, where even in places that aren't low lying, can flood, even the tops of hills can flood because the water just falls so fast, doesn't have time to wash off. So just the last few minutes, I want to talk about forecast and warning issues, because I think those are interesting and were problematic in Ida. So this is an article, a headline from the New York Times the day after, where Mayor de Blasio, no longer a mayor, but he was at that time, said that kind of blamed the forecast. So all these people died in New York City, mostly in cars, by the way, that were flooded on the road, or in basement apartments. That's where most of the deaths were. And people asked the mayor, what happened? Why did we get it wrong? Why did all these people die? And he said, well, he blamed the forecaster. He said, we get from the very best experts projections that are then made a mockery of in a matter of minutes. And a lot of forecasters pushed back on this, and rightly so, because it's not really a fair statement, but it's a little bit fair in ways that I'm going to try to explain now. The mayor was wrong, but he wasn't totally wrong. So here's, to show why I say he was wrong, this is a forecast from Monday. So Ida hit Wednesday night into Thursday. That's when the really heavy rain was. Remember, it made landfall in Louisiana on Sunday, hit here Wednesday night. And so this was the weather forecast for Monday from the Weather Service, showing the forecast rain map for the total Wednesday evening through Thursday evening. So, look at it. I mean, this is very, very accurate. You see these numbers around 4, 5, 6, 7 inches in exactly the strip where they were observed. I showed you the gauges before. This is a forecast from 2 days ahead of time. Pretty darn smack on. So to say the forecasts were wrong at first glance just doesn't seem true. Weather Service nailed it. If you look at this map, you'd have to say. Here's a more detailed map from a graduate student named Tomer Berg. I don't know him. He's a very smart guy, posts these things on Twitter, and I just grabbed it, so credit to him. But he's showing how the forecast changed over time. So this is 3 days ahead, 2 days ahead, 1 day ahead. The forecasts were getting even more and more extreme for New York City and Philly. So, and here's some of the observations. Down here, I think, is the observation. So, another indication of that the forecast was right in predicting heavy rainfall. Here's another map from the same guy. Here's some Tomer Berg, very savvy interpreter of the forecast, showing the area of highest concern, saying there could be 4 inches or maybe even 10 to 14 inches. But notice, he's not saying how long it's going to take for the rain to fall. And I'm not picking on this guy. I think he's one of the best people out there explaining it. Neither the Weather Service nor any of the private sort of experts that I saw really emphasize the hourly rainfall total. And I think there's a reason for that. It's that it's hard for our weather forecast models to get that right. It's one thing to trust the weather forecast saying, where is it going to rain a lot? It's another thing to ask how much is going to fall in a single hour. That's a really, really demanding thing. And so even if the models say there's going to be 4 inches in an hour, we don't necessarily believe it. We certainly aren't necessarily confident about where that's going to happen. So there was all this stuff showing quite accurately the total rain, but not necessarily those hourly amounts, which are what caused the problem in New York City. Now, as it happens, since we're talking about emergency management, it's good to talk about what's actually being done in New York City. Maybe there's even somebody who was involved in writing this on this call. I don't know. But the city had just put out a few months earlier this stormwater resiliency plan. So the city had been studying how to manage its stormwater and thinking through exactly events like this and how to prepare for them. So here is a page, cut and paste directly from that report. A bunch of city agencies were involved in producing this, including the Office of Emergency Management. And they kind of thought through couple of scenarios, and their most extreme scenario was roughly 3.5 inches of rain falling in an hour, also referred to as the 100-year storm. Now, that's what happened in Ida. I just showed you the data. So they're imagining it could happen with 4.8 feet of sea level rise, blah, blah, blah. But basically, they're imagining an amount of rain that happened in Ida. And they're saying it would cause damage and disruption. It would disrupt the subways and regional rail, cause flooding. All these things happened, of course. And among the recommendations were that the Office of Emergency Management, which New York City has a very, very good Office of Emergency Management because we're a big city and we've had a lot of big disasters, 9/11, Sandy, et cetera. So we have a lot of practice, a lot of very talented people there. And one of the guidance from this report was they should develop plans for how to warn people in basement apartments. So they knew that would be a problem, but this report had just been written. It was hadn't yet been time to really act on it. And so, just to say that, so they did some modeling though. So this is the modeling for that that extreme storm that produces 3.5 inches of rain in an hour. This is showing where it's going to flood. I don't want to interpret this in detail. The blue, and the red shows flooding, but just to say that a lot of this blue is not in all, the low-lying areas like down here in Staten Island and here in Jamaica Bay, that all flooded during Sandy, that's low-lying areas. But a lot of these other areas in the interior are not places that would flood in anything but a flash flood. This is due to the intense rain. Just to say it's this had been studied, and I haven't seen this explicitly compared to the outcomes, but just to say that it's a different flooding pattern than you would get from something that's not a flash flood, from something that's happens a little more slowly. But anyway, scenario had been modeled. And here's just some summary thoughts I want to give that maybe we can talk about afterwards. I think the extreme rainfall and flash flood risks for the New York Metro were pretty well predicted, at least a couple of days ahead of time, maybe arguably longer, 4 or 5 days even. We knew the hurricane was going to come over us. But I don't think the risks of record breaking, and they were record breaking. I don't know if I said that, but many, many records were broken by those hourly values and some of the daily values too. And I think the risks of those high hourly, the condensed, really fast, heavy rain totals were not emphasized in the forecast, maybe because it's hard to predict them with confidence and people don't want to, get it wrong. So they just predict, talk about what they're more confident about. and that's just the state of the science. The city government had started to think through quite clearly and quite thoughtfully what would happen if we had an event like this, but it hadn't happened, not in at least the last 100 years. I mean, this 3.8 inches in Central Park was a record breaker, and there's data there going back to the 19th century. So maybe even though the mayor was being told, that this is a huge rain event, maybe it hadn't gotten all the way through to communicating, we could have 4 inches in an hour and that would kill people in basement apartments and cars on roads. So we should take specific actions. So that's in the sense in which maybe the mayor wasn't totally wrong to say that he hadn't been, not everything had been perfectly communicated to him, but that's the state of the art. So this is my last slide, really. These are some broader questions that I wrote them thinking about Ida in New York City and what happened, but I think they're relevant much more broadly to a lot of other kinds of extremes events. And I think some of them are relevant to emergency management. So one is, when we think about an event like this, what's the probability of it? What's the return period? So that report said Ida was a 100-year event, but whenever an event happens, it's good to know that, because that's given us some idea as we want to plan for it. Is it like complete freak of nature, or is it something that, is likely to happen sooner or later? How should we think about that? And how is that probability changed? To what degree is that probability influenced by global warming? And how much is that changing the future? If it used to be a 100-year event, is it now a 20-year event? That's what scientists like me are working on. And I spent the first half of the talk talking about that. And, that's science question. I think a practical question for emergency managers and other policymakers, other decision makers, government officials, is how much money should we spend to prepare for events that are low probability but high impact? Something that's a 100-year storm, maybe a 500 or 1,000-year storm, but it would be super catastrophic if it happened. Category 3 hurricane hits Boston. Never happened, might never happen in the next 100 years, but if it did, it would be really terrible. How much should we prepare for those kind of things? It's a tough judgment call. How can we prepare infrastructure? Flash floods are different than other kinds of floods. So in New York City, for example, we depend on our subways. We know that the low-lying parts of the system are going to get flooded, but in events like this can even flood the not so low-lying areas. So, how should we prepare for that? And I think this is really a good question for weather forecasters and also emergency managers, is how to warn people effectively without causing cry wolf syndrome. Because this is the last point I want to end on, is that the scientific information is always uncertain. If we're giving a forecast, whether it's a long-term forecast of global warming, if for the next decade or the next 100 years, or we're giving a forecast for a storm that's going to hit in 2 days, we never know exactly what's going to happen. There's always some error bar, and you want to prepare people for the worst case scenario, because the worst case scenario is going to be a lot of people die if they don't evacuate. You want to communicate that, but because there's uncertainty, it means that sometimes you're going to be wrong. People are going to evacuate, and then it's going to turn out that they feel like they shouldn't have had to because the storm wasn't that bad. But then next time they might not believe you. But that's inevitable if the information is uncertain, and but the worst case scenario is something you have to prepare for. So I think that's a generic problem that we have to think about as we communicate these risks based on the best scientific information we have. So that's all I have. Thanks for listening. I'm just closing here with some plugs. This is my book about Hurricane Sandy, which talks about what happened in that event, how climate change affected it or didn't. It's a complicated story. But also a lot of other broader details about the science and about policy and how we think about risk in the long term. And then I have a podcast, as mentioned, it's called Deep Convection, and I talk to other climate scientists. Mostly, sometimes we talk about science a lot, but a lot of times we talk about people's lives and careers and even political things and climate change. So, and everybody's feelings about that. So I'll stop there. Thanks so much for your attention. And I think I will stop sharing the screen, right, Todd?
Yes. That's always the trick, right? So, well, thank you for the great presentation, and yeah, I do encourage everybody to buy the book and also take a look at the podcast, because I think the more you know about this critical, basically what we're going to be dealing with in the next 10, 15, 20, well, in our lifetime, but I mean, professionally speaking, 10, 15, 20 years, you're going to have to know more about climate change and the impacts that it has. There we go. I just saw the thing. Thank you so much for letting me know you couldn't hear me. And yeah, I am a professional at this. I know how to unmute my microphone. I was saying thank you so much for everybody and Adam for doing the presentation. I do encourage everybody to purchase the book. and to take a look at the podcast and learn more about how climate change is really impacting us on our profession. Because for the next, professionally speaking, the next 20, 25 years of your profession, collectively speaking here, that we're going to be dealing with the issues from climate change. And I do have some questions that I wrote down that I got from this, but I also want to get into the questions that the listeners have. But before we do that, Chastity posted in the chat here as the current vice chair of the new caucus that has been created specifically for climate change. And if you guys want to get involved with that caucus, I think it's a critical one, like I said, and getting involved would be a great way. And if you're an IAM member, it's a great caucus to be part of. If you're not an IAM member, you can join and join the caucus. I'm sure she'd be happy to have you on there. So let's get some questions here. The one I have here, though, this is the one I wrote down myself, is on coastal flooding. And you mentioned the idea that coastal flooding is a problem. We all know it's been a problem. Katrina is a really good example of something that really went sideways with the levees not working and the protections that were built not working. However, it sounds like that the storms, that we're not necessarily worried about the wind event as much as we are about the rain of the flooding event. Is that, am I hearing that correctly from you?
It depends where you are, and it depends on the storm. So there's three ways that hurricanes cause damage. There's the wind, which can obviously knock stuff down, destroy stuff, and send things flying through the air, rip the roofs off houses. There's storm surge, which is like what happened in Sandy and Katrina. That was the main problem. That's the wind blowing the water from the ocean onto the land. So it causes flooding, but not from the sky, but from the sea. And then there's rain, which can cause flooding. All three things can kill people and harm property and infrastructure. And which risk is highest depends on where you are. So in New York City, for example, we're pretty unlikely to get a Category 4 or 5 hurricane here. The strongest ever that we know of is Category 3, which hit Long Island. That was the Great New England Hurricane and the Long Island Express. That didn't hit the city directly. Sandy was kind of barely Category 1 according to the wind, but because it was so large, it was created a huge surge. So I think in places like here, where we're not really tropical and we're not going to get the very highest intensity storms, or at least in the current and near future climate, we're unlikely to get those high intensity storms, but we have lots of low-lying areas. It's the flooding that's a bigger problem, and it can be surge or rain. But in a coastal city like New York, I think we knew even before Sandy, there had been reports written going back decades that identified that surge was the biggest risk. And that's true in other places too, but wind can be tremendously destructive. So if you think about Typhoon Haiyan in the Philippines, that was in 2013, the year after Sandy, that was a catastrophic surge event. It killed about something like 6,000 people, by the way, way more, like 4 times Katrina, but 4 or 5 times Katrina death toll. A lot of that was surge, but that was also incredibly powerful winds that would have destroyed lots of property, by itself. And there's other places where rainfall, flooding, is the big risk. So like Hurricane Mitch in, I believe it was 98 in Central America, that was like flooding, rainfall and landslides. And there's been many catastrophic events like that. So all three can cause damage and loss of life. And in some places, all three are hazards. And in some places, one is more likely, than others.
And the public policy side of things, I mean, like, obviously with wind events, we could create building codes, if you think about that, to mitigate that. But then there's public funding that would have to go into dealing with a storm surge, whether it's barricades or whatever seems to work in that particular area. So it's kind of a dual point thing. One is going to be impacting people's homes and building. The other one's really coming out of public funds. So Nate asked a question. Nate Matthews just says, this kind of goes along the same lines of what we're just talking about, is how accurate are the hourly rain total forecasts compared to daily rain forecasts?
So that's a good question. I've never seen an assessment of that. I don't, maybe somebody's done it. But to my knowledge, the Weather Service doesn't even routinely issue hourly rain forecasts. By which I mean, of course you can look on your phone. I mean, if you use any of the commercial weather apps, like I use there's weather, any of the big companies, whether it's Weather Channel, AccuWeather, there's all these apps you can use, and they will give you hourly like probabilities of rainfall, but I haven't seen routinely issued forecasts that are sent out to the public that tell you how much rain will fall in an hour, and not just a probability, but like how many. And I think that's because our models, our weather forecast computer models that actually predict the rainfall explicitly, they'll produce those numbers, but I think the forecasters aren't confident enough in them, especially like where it's going to happen, to say like, so you could produce a forecast to say, what's the peak rainfall that's going to fall in Central Park? What's the most hourly total we're going to get for this storm? So you could do that, but I think we don't routinely do it because there isn't that much confidence, and we're worried that we get it so wrong. So I don't know the answer. I've never seen it assessed, but I'm pretty sure the hourly totals would be less accurate than the daily totals. And even the daily totals are not that great. Generally, rainfall, quantitative precipitation forecasting, we say in the business, is a tough thing. It's gotten a lot better than it used to be, but the finer scale you try to do it, the harder it is, and hourly is finer scale than daily.
So along those lines with the rainfall and predictive stuff, so we're not worried necessarily about the frequency of storms coming in. We're just worried about the intensity of the storms coming in. So maybe with climate change?
I wouldn't say we're not worried. I would say it's a big uncertainty. So globally, we don't know why the number of tropical cyclones reaching tropical storm intensity or greater each year is about 80 or 90 plus or minus 10 or so. We don't know why it's that number and not 200 or 300 or 20 or 30. And not knowing that, we also don't know whether it should go up or go down with global warming, and our different models give different answers about that. So, but it's quite possible. I mean, the different models all predict some change, they just don't predict the same change. So we don't know. So there could well be places, in fact, I wouldn't be surprised if there weren't some places that see a lot more hurricanes in the future than they did in the past. Some places might see less. We just don't have that much confidence in it. So but the storms we do see, we expect that on average, they'll get stronger in terms of wind and rain, so as well as coastal flood risk. So there's definitely some respects in which risk is going up. It's just that, we can't rule out that in some places you might have worse storms, but not as many of them. So, figuring out what the total risk is hard to say. But I think from emergency management point of view, a thing I would say about all extreme weather events is like, if I tell you they're going up 10%, in the next 30 years, I don't know what you do with that information. It's not like, I don't know how like precisely one can plan for that. I just think like we have to be prepared for a wider range of possibilities than we would have in the past. We're going to see more and more things that we weren't expecting or hadn't historically seen. And that's always going to happen anyway, even if there's no climate change, because sometimes just rare event happened that hasn't happened before just by chance, but that's going to be happening more. And maybe we can't always put our finger on exactly which one you should expect. We can give some guidance about that, but some things we're uncertain about. But I think it's reasonable to say that like the range of possibilities of things emergency managers are going to have to deal with is getting bigger.
Mark also has a couple of questions, and I'm going to kind of combine them, Mark, just for brevity. So they're more policy and political questions, I guess, if you will. And one is we'll start. How does this data impact the policy and politics? And I think I can make a stab at that one as well. And then looking at comparisons between fires in Mexico and California, these discussions provide various theories regarding California wildfires. And I think that's more of a policy question as well of how do we manage climate change, and how do we manage some of the forestry issues that are going on? And I think that's where we're kind of getting with it. But let me make my first stab at the policy question, and then Adam, I'll let you take a stab at it from the data side of it. So, yeah, I mean, all data impacts policy and politics, if you will. And my contention has always been that disasters are all political. What I mean by that is, as you can see, the Mark's or Adam's quote of the mayor, the question came to him, what did we do wrong? And he kind of pushed back onto the scientists saying, no, we didn't get the right information, which obviously was wrong. As far as his assessment of that, politicians lose their jobs a lot over these bad policy decisions. We could go to Katrina and take a look at what happened with Ray Nagin after his missteps on that. So yeah, the data analysis and making decisions are hugely political. On the policy side, when we start taking a look at what we're doing, specifically where we're spending our resources, and the resources are money and time, and I think that Adam brought up a good point of, do we plan for that one-off storm that might hit, Boston in 100 years from now? It's a question for the community, number one, but it's also, where do we want to spend those resources today to fix the things that are going to impact us on a regular basis? And I think that's kind of where I would go with making decisions based on this and how that helps with policy. Adam, what do you think on that?
Yeah, a few things. So I'm not a policy expert, and I don't want to give very precise guidance. I don't have an answer on whether we should worry more about the 100-year storm or the 500-year storm, for example. I think that's a tough judgment call, but I think there's a couple things we could say. One is that in many places, maybe even most places in the world, including the United States, we're not that well adapted and prepared for our current climate. Even without climate change, we have a lot of people living in very high-risk areas that, all else equal, they probably shouldn't be. We don't want to blame those people. They're not like they did anything wrong, but it's just to say we have a lot of policies, both around insurance and zoning and other things, that have encouraged a lot of people in infrastructure being in harm's way. And even without climate change, there's a lot of things we could do to be better prepared and less vulnerable. So including some of the most at-risk populations, which were often the most marginalized and poorest people. So I guess what I'm saying, there's a lot of low regret actions. It's not like we're saying that because of climate change, we should do all these things that then, if it turns out not to be as bad as our models predict, then we'll have wasted all the money. I think there's a lot of things we should do anyway. And in a warming climate, it'll be good to have done them. Now, there's some things that are outside that, things like sea level rise are definitely outside the range of just what we would, there's places that would have been fine, and the historical climate wouldn't have flooded that often. And when it comes, 50, 100 years from now, they might be flooding every day, the lowest lying places, Virginia Beach and so on. That's a different story. And there we have to really, the climate change is a huge factor. But I think in other places, I don't want to underplay the climate change part of the story. I spent a lot of my time trying to quantify it, but I think there's a lot we can do that's relatively low regret. I can't remember if there was another part of the question.
No, I think that's it. I think there's more on policy. And I agree with you there. We could do some certain things that would benefit people regardless if it's climate change or not, and make their life a little easier, and I think.
The other thing to say is, the civil engineers will tell us that the U.S. is chronically underinvested in infrastructure. We have a lot of infrastructure that's falling apart. And so we should be fixing that stuff anyway. And while we're doing that, there's a lot of opportunities to make it more resilient.
Yes.
Against extreme weather and climate change.
So Joseph asks, he goes, recent research focusing on Hurricane Harvey highlighted the role of urbanization. Yes. With the flood response, the storm total rainfall in Houston. That's a whole other story about that one. And then do you think urbanization played a similar role to flooding that caused the remnants of Ida in New York and New Jersey?
Yeah, that's an important point. Yeah, so it's true. If you want to think about how did human activity affect the flooding in Hurricane Harvey, there might be a little bit of it might have been climate change, but much more of it was due to this fact that we have built in a lot of low-lying areas. In some places, there were areas set aside for reservoir, and you weren't supposed to build in it, and people put houses right in the floodplain that the engineering drawing said don't build here, don't build here, and people did. So first of all, it's two things. It's one, it's putting houses in the floodplain, and it's also just paving the floodplain so that the water, has nowhere to go except into the streets and homes. Definitely was a big factor in Harvey. In the Northeast, absolutely is a factor here too. Look at New York and New Jersey. It's New York City, where I live, is the most urbanized place you can possibly be. It's the most impervious surface. I think the difference between here and Houston is that urbanization happened a long time ago. Houston, it's sort of been happening over the last 50 years that it keeps sprawling and being built up. Here, it's already a done deal. So yes, there would have been much less flooding if we were farmland than if we're all concrete. But we've been concrete for a long time, so that's a situation we're in. We have to deal with it. I mean, it's, we can't really go back to farmland here. So yeah, I mean, it definitely, absolutely, it's a factor. And in the short term, I think those kinds of things are a bigger factor than climate change. But in the longer term, climate change is going to become a bigger and bigger factor.
Yeah, I was just lecturing last night on this, on the Harvey question too, and it baffles me to this day. Viv Lee asked, thanks, Adam. Great presentation. What's your research general understanding of your QN3, and how much should we spend on the outlier events? So we sort of talked about that. I think that's been question 3. But how much time should we be spending on those outlier events?
Yeah, it's a good question. I mean, because I don't have an answer, but I can tell a little story about Sandy. And if I guess this is an ad for the book because I wrote a lot of pages about this. But if you look at what happened in Sandy, there were reports written back as early as the mid 90s. In about 91, I think it was, maybe it was 92 or 93, there was a big winter storm here that produced a lot of rain. It flooded the subways a little, and it got people worried. And there was a report put out, it came out in 95 by the Army Corps, Weather Service, and some other local agencies. And it was flood risk for New York City in a hurricane. And they knew storm surge was the big risk, and they made maps of like where the worst, highest surges could be. The Hurricane Center took some guesses as to what would be the biggest storm that could hit here and what the surge it would cause. And then they took a topographic map and they said, how high could the surge get? And then they put that on top of the transit facilities, and they showed a whole bunch of transit facilities that would flood. One that I like to talk about, because it was rebuilt, I like to talk about the South Ferry subway station, which is the one by this where you get the ferry to Staten Island, and that's the south end of the subway line I live on. And that it showed how that station would totally flood in a Sandy type event. And that station actually got rebuilt in 2000. It got finished right before Sandy in 2012, and it was built in the same place, exactly the same flood vulnerability. And 20 years before, it was known that this was a risk. So in other words, I think what it shows is that it's like we knew this would happen, and we couldn't put that much of a number on it. Some people had estimated maybe it's a 200-year storm, or maybe it's, there hadn't been a storm that bad since at least 1821 for New York City. We know that. So it's something like, a couple 100-year storm. But we have a city of 8 million people, and, we suffered tens of billions of dollars of damage from that. So should we have been prepared? I think we should have been. I think we had enough information. But it shows why it's hard, because the political cycles are a few years, and it's hard for anybody to justify political capital and taxpayer money to make a big investment in something that sooner or later it'll pay off. Everybody tells us, there's research that shows that if you spend $1 to prepare for a disaster, you get back in the long run several dollars, maybe $10 in relief that you don't have to do. In the long run, it pays off. But if I'm in charge for 4 years, it's probably not going to happen on my watch. So it's hard for me to spend to justify spending my political capital, on that. When if the disaster happens, I can just go and try to get relief money out of Congress and help people and look better. So I don't have an answer to how we should do it, but I do think that it would be great if, as a society, we could learn to think a little bit longer term and prepare for longer term risks, because climate change is nothing but that, right? I mean, it's already changed. The climate risk have already gone up, but it's getting worse. So, I think somehow humans have a propensity to only think about things they've seen recently. There's the psychologists have books about this. It's the problem we all have. I'm the same. If it hasn't happened to you in your life or recently, it's kind of hard to imagine somebody says but we do have ways of doing it, right? We buy insurance against our house burning down. It's probably not going to happen. So, but we do it anyway. So we have to somehow build up systems that enable us as society and as a species to think a little bit long term. So that's kind of dodging the question, but that's the best I got.
We're right at our cutoff time. We do have a few more questions that we have here. I don't know if you mind staying on for a couple and answering these questions, or if you got to run. If you could share your contact information if people want to reach out to you to ask questions, that would be great. If you would like to do that. You want to run through these questions really quick, or do you have to go?
I can do them real quick. I got students I got to talk to, but we can do them fast.
Okay, this one's really quick. I think you have the answer for this. He goes, they said, Adam, can you please clarify? I did not understand correctly that climate change will increase the percentage of rainfall. That was from Mark.
The percentage of rainfall. So it's the way we think about extreme rainfall events is that for each degree of global warming, the heaviest rain events go up by 1% of what they were before, which means it's like an exponential increase. It means that instead of saying for each degree, we get another half inch of rain, or instead of measuring it that way, the way that is more, the science tells us we should think about it is that for each degree of warming, the heavy rain events get heavier than they were before by a percentage. And that means that as you warm, each degree of warming gives you a bigger increase, because you're increasing the percentage of what it was the degree before. So it's just, a sort of baseline number is 6 or 7%, but it could be more than that. It could be less than that. It could be, especially for hourly rain events, could be more. And it might depend on where you are on the planet, but that's kind of a ballpark.
Right. Larry has a statement more than a question. Structural protective efforts and costs. Japan's tsunami construction of the new and massive seawalls might be worthy study, although not climate related. It's interesting to see what they're doing there. And that's absolutely. And Japan has really been always pretty forward thinking when it comes to seawalls. And when I lived over in Japan, we used to walk them all the time. It was very interesting. It's been there I was back there in the 90s, so they've been doing this for a long time.
Yeah.
Is there a conflict between the observed change in heavy participation slides that you showed and how the West is getting drier? It's a good question.
Yeah. So heavy rain events, what I was talking about is precipitation extremes. So in other words, when the rainfall event, we're having more rain falling in concentrated events. And that does somewhat imply that then you have longer dry periods. But for the US Southwest, and so what I showed, the rainfall change map from the climate models, I showed there's a lot of the planet where the models disagree about whether it should be getting wetter or drier. The US Southwest and northern Mexico is one of the places where they agree. And actually most of the models, if not all, show it getting drier with climate, as has in fact been happening. Now, the specific droughts we've been having in California, my latest reading of the literature, as best I understand it, is that those droughts have not been strongly attributed to climate change, in the sense that what the models predict for California is that the rainy season will get a little shorter, but more intense when it happens. And the shoulder seasons will, compress a little bit. And the droughts that we've seen over the last couple of years, the absence of precipitation, my reading of the climate science literature, which I'm not an expert, but I have some colleagues who are, and I try to follow what they're doing, is that they don't blame those rainfall deficits in California specifically, maybe different for Arizona and New Mexico, but in California specifically, they don't blame it on climate change. However, they will say that because it's hotter, once you have a precipitation deficit, you're evaporating the water that's in the ground more. So we talk about meteorological drought, that's when it doesn't rain, and hydrologic drought is when you don't have the rain in the surface, in the reservoirs and in the streams and in the soil. And so, in other words, hydrologic drought, I think we do have a climate change signal even in California, and in meteorological drought, it's unclear because there's a lot of natural variability. So it's a little bit of a mixed up story. And my understanding, again, don't quote me, but if I could, is that the the Southwest and northern Mexico is a little clearer drying signal, and California is a little more complicated, but the heat is drying it out everywhere and causing the fire risk to go up.
Right. Rosanna asks, would it be helpful in your opinion for local emergency managers to be able to have a bi-directional communication mechanism with utilities? So hazard mitigation plans and resilient planning at the local level can be coordinated with large-scale utility planning. I'll take this question. Absolutely. Yes. That's a astounding. Yeah, we need to have better communication between utilities and the local government, and coordination of efforts when it comes to emergency management issues that we have. Adam, any thoughts on the quality and gaps of currently available to impact models by catastrophic modeling companies?
Yeah, hi Doug, we know each other. That's a setup. I don't want to talk about specific. So what he's talking about is the catastrophe modeling companies, the companies that provide risk assessment information to the reinsurance industry, and we'll just say that I don't want to critique any particular companies. I'll just say that I think by and large, there's plenty of things we could talk about with those models. They're very important tools to use to estimate risk, and we should be using models like that for a range of other purposes, not just reinsurance. But historically, I think those models have been based on historical data very closely, which means they're backward looking. They don't directly incorporate climate change. And so that means that they're even not fully capturing the climate change risk in the present, because they're looking back in time and including all the data and estimating the risk from that. And I think to handle climate change, you really need some amount of forward physical modeling, which is a different can of worms. And everybody's scrambling now to try to do this because there's a lot of demand for it, not just in the reinsurance industry anymore, but also in the broader financial sector, where people are now thinking they're going to have to disclose climate risk and trying to figure out how to do that. So, I mean, this is an active area of science. I think that not only should the risk model companies be working to incorporate climate change, which, I mean, they're starting to do, but they're late getting around to it. But academics like me, I think I'm trying to advocate that more of us should be doing this kind of practical work that's not just understanding the climate system writ large, but trying to focus in on how it affects specific human risks. I think we could do more of that. So, yeah, I mean, that's about it. I think that's about as specific as we have time for.
All right, I'm gonna ask one last question, and then we're gonna let you go. Are there any attribution studies to the climate change to Ida?
Not that I know of yet. That's a good question. We've now got to the point that we can do these relatively quickly for some kinds of events. And so sometimes they even come out within days of the event. But for Ida, I don't think I have seen one, but it could be done. And it might happen that I just don't know it.
Adam, thank you so much for your time today, and I'm going to turn it back over to Holly for close. Jason, I know you have a good question right there. We'll get to that. That's a policy question, and Diana as well. We'll get into the policy questions, and I'll take a look at those and get those back over to you. But Holly, back over to you.
Okay, I'm going to turn the video off, right?
Yes.
Okay.
Oh, Todd, it is all you. You get to share our survey link as the last couple items we have, as well as mentioning our upcoming webinar.
Oh, okay, perfect. Sorry about that. Yes. So first of all, I want to just really thank Adam for the time he spent with us this morning, and all of you for spending time with us afternoon, I suppose, and for all of you for spending time with us as well. And I know that we have lots of questions when it comes to this, and a couple we couldn't get to, and we'll try to get those questions to you this May. On the 19th is our next webinar. Join us for the topic is where will people go? Climate-induced relocation from retreat to migration with guest Patrick Merchman. That is going to be an amazing conversation because we're already starting to see climate refugees today, and I think it's just going to get worse. And Patrick, I know you're here. I'm really looking forward to that conversation as well. And climate-induced relocation scales from individual homeowners, the buyouts, and a whole bunch of things like that are going on. It's happening internationally. It's even happened here in the United States. So this is definitely something that we should be really taking a look at. Also, please, you can register for that webinar right now. I think it's in the comment section. If you can take a look at that, register for next webinar, and as well, please take a look and do the webinar survey, and you can also receive continuing education credits for this event. Also, take a look at us at LinkedIn, at our company page over there, the SpeaknSpark page, and also the Emergency Management Network page. And please subscribe to our Substack for newsletter so we can share this information with you as well. And again, thank you for participating, and we'll see you all on the next one.